Variable Control Charts, Chapter 5. In this chapter, we're going to review the concept of variation. We are going to understand the control chart method, its objective, and the control chart techniques, and understand the state of control concept. So variation is a law of nature, and it means that not two natural items in any category are exactly the same. We can have variation that might be quite large and easily noticeable, such as the human height, or we can also have variation that might be very small, such as the fiber-tipped pins or shapes of snowflakes. However, the important thing here is to identify and to understand that we have variation, that they are type of variation, and we can control the variation. In prior lecture, we explained that there are three categories of variation in a piece-part production. These are within piece variation, which is things that can be noticeable and could be in the surface of a piece or etc. We can also have piece-to-piece variation, and this is the type of variation that occurs among pieces produced at the same time. And also we have time-to-time variation, and this is a type of variation that we can see in a product or service produced at different times of the day, for example, different shift. So in this variation concept, because we have different type, we have also to understand that we have different sources of variation. We can have sources that can be part of the input, such as materials and tools. We can have sources of variation that are coming in the transformation process, such as operator, methods, machine, environment. And also we can have sources of variation in an output, such as the measurement instruments, the human inspection performance. So these sources of variation can help us to understand that what those that are common causes of variation that are there that we can predict and control, and also what are those that are special causes of variations, and for those we need to apply corrective actions and eliminate the root cause of those, because those are the ones that are unpredictable and can cause harm in a process. So in this slide, you can also see that the common causes of variations are predictable over the time. And because they're predictable, we can control it. Now, those are the special causes of variations. They're not predictable over time. You know when they're going to happen. You can see that it's very hard to predict them. So those are the ones that are causing harm in a process. Now, when we see this type of variation, or a good method to determine variations is using the control chart method. Okay, and they're used to indicate when observed variations in quality are greater that could be left to chance. A control chart could help us to understand if a process is in a state of control or not. A control chart has some limits. It has an upper control limit and a lower control limit. And once you graphic your process, you can see if that process is within the control zone, or it has a new zone and you can see improvement, or you can see if the process is out of control. So the objective of variables control charts are quality improvement, to determine the process capability, for decisions in regard to product specifications, for current decisions in regard to the production process, and for current decisions in regard to recently produced items. So it can help you to understand and correct your process prior to producing the product, or once the product is produced, also can help you to make sure that the customer gets the right product with the right quality. So this is how a control chart looks like. You will have time. A control chart is always over time. You can have your specific characteristic that you measure, or specific sample values, and then you will always have an upper control limit, and is called the UCL. You're always going to have a lower control limit, which is the LCL. You also are going to have a average value, which is the average, and you're going to have your sample value, which is the one that you're going to graphic. And based on this behavior, you can, in this case, determine that you have a point or 2 points that are out of control, actually a third point. So you have 3 points that are either above or below the lower or the upper control limit. And you can, based on this, you can say that you have some outliers, so you have some indications that your process is out of control. Now, why wouldn't you use the histograms? And the thing with the histograms is that the histograms do not take into consideration changes over time. And control charts, they do. They can tell us when a process changes. Now there are different type of control charts. We have variable control charts and we have attribute control charts. And this depends on the type of data that you're using. So if you're using continuous data that you can measure, you can break into decimal places, you use the variable control charts. And if you have discrete data that can only be counted, you use the attribute control charts. The variable control charts are more sensitive to a shift in variation or mean than the attribute control charts. Also, the numerical values can be obtained for the quality characteristic. You can say, well, transform or convert a good quality characteristic into numbers. And it's usually used at the machine and or operator level. The attribute control charts, and this is going to be another lecture. When you have attribute control charts, a numerical value is not specified for the quality characteristic. Because remember, in this case, we have defective or non-defective, or conforming or non-conforming. But this one is used for transactional or white collar processes. Some of the commonly used control charts are for the variable data, the X bar and R chart, or the X bar and S charts, or the charts for individuals. And for attribute data, you have chart for defective, which is the P chart, the NP chart, or for defect, which are the C chart or the U chart. So the control chart types that you're going to use will depend first in the type of data that you have. So if you have continuous numerical data, you know that you have to use variable charts. If you have categorical or discrete numerical data, you're going to use the attribute chart. Now, within those two categories, you also have different charts, and these will depend on the sample size, or either if you have, in the attribute case, if you have a defect or you have defective pieces. So which one to use? In the case that you have variable data and you have a large sample size, you will use the X bar and S char as is indicated in this branch. If you have small sample size, which I will say that n is equal or is less than 10, you will use the X bar R char. If you have a sample size equal to 1 is where you use the X char or the moving range. For the attribute, having the number of defective units and having a constant sample size for each one of your data sets or group, you will use either the P or the NP char. If you have variable sample size, you will use the P char. For the number of defects, having a constant sample size, you will use a C or U char, but if you have variable sample size, you will be only able to use the U char. So some of the techniques of the control chart is as the subgroup size increases, the control limits become closer to the central value, which makes the control chart more sensitive to small variations in the process average. And this is true for everything that we do. If we use a larger sample size, we're going to get closer to our population size, and that will help us to obtain more accurate information about the population. Sometimes that is possible, sometimes not. So you have to understand that. We work with subgroup in control charts. It means a group of data that is going to be part of a subgroup. Okay. If the subgroup size increases, also the inspection cost per subgroup increases, and this is the disadvantage of having big sample size. Also, if you're using destructive testing and the item is expensive, you should use a small subgroup size so you're not wasting a lot of money. Control charts, as I said before, part of the objective is for decisions. Okay, so the setup decision works this way. You have to define the type of chart that you're going to use, and this will depend once again of the data that you have to use. Then you define the quality characteristic. The way we sample should either maximize the differences between samples or minimize the difference within samples. And we might need separate control chart for different situations. If you're trying to use it for operator, for machine, or for vendors, you should separate them so it's clear the type of characteristic that you are evaluating. You determine the sample size that you're going to use, and you must also consider the cost of the inspection or testing, and this is part of the determining the sample size, the cost of shipping or a non-conforming item, or the cost of providing subpar services. Then you have to calculate the frequency of the sampling, and based on that, the frequency will decrease when bringing process in control, because you don't have to do it that often. Your process is under control, so you might have to check it less often than you used to. Also, the choice of measuring instruments, and this will depend the accuracy and the use. And you have to design a data recording form or software to collect that data. So once you have your control chart graphed, the next step will be to analyze it, okay? And when we analyze it, we are looking to understand if the process is in a state of control or not. If the process is in control, you could also have errors, and this is part of any variation that the concept of variation that we have, okay? So, there are two types of error. Type 1, which is this one occurs when looking for those special causes of variation, when in reality we only have common causes of variation. So in this case, we don't have to apply corrective actions because something that we can predict. The type 2 error will occur when assuming that you only have those common causes of variation, but in reality you have special causes of variation. So the type 1 error is also called alpha. Okay, and once again, this is inferring that the process is out of control when it is not. And the type 2 error is called beta. And this is the error of not detecting a shift where there is a shift in the process mean. This means that you're inferring that the process is in control when in reality it's out of control. If you graphic the error, you have all your normal distribution curve, okay? You have your upper control limit, your lower control limit, and your average. Remember, the average is always located in the center. Whatever is after the above the upper control limit or below the lower control limit is your alpha, which is the type 1 error. If you have a type 2 error, it will be in between those upper and lower control limit. And this is because you're thinking that everything is under control, but when in reality is not. So when a process is out of control, it means that you have outliers. You have numbers that are above or below the upper and the lower control limit. Also, a process can be out of control even though the data is all your subgroup of data are within those upper and lower control limit. And we're going to see them in a second. So a process is out of control when a point, which is a subgroup of values, falls outside its control limit. What it means when a process is out of control is that a change in the process has occurred. And this is due to special causes of variation, things that we couldn't predict, so we couldn't control before. Now, a process can also be considered out of control even when the points fall inside the 3 sigma limits. And this is either 3 sigma above the average or below the average. And this is because we could have patterns in data. So control chart patterns are a natural pattern is one that has no identifier arrangement of the plotted points. It could be that no points outside of the control limits. It could be the majority of the points are near the center line. You could also have that few points are close to the control limits. Or you have a stable system of common causes. Or it could be that the process is stable. Now, the typical out-of-control patterns are that points are outside of the control limit, sudden shift in process average, cycles, trends, hugging the center line, hugging the control limits, or instability. So this is how a pattern looks like, and this is the patterns that you should look like in control chart. This is a normal behavior. You have points that are either above or below your average or your target value, and they're not outside of the control limits, either the upper and the lower. Okay, now this is a out of control process because one subgroup, one point is above the upper control limit. This is also an out of control process, and it's because we are observing trends. And you can see that it's in either direction. 5 points in a road this is will indicate that you need to investigate for special causes of variation. Also, if you have two plots, two subgroup, 2 points that are near the lower or the upper control limit, this is also an indication that you have to investigate for special causes of variation. Having 5 above or below the center line is also an indication that you have to investigate for special causes of variation, or if you have erratic behavior. Another type of pattern is when there's a shift in process average. And you see that in this case, the data were either above or below, but after a certain time, everything has shifted. So now everything has moved. So this is an indication that your process could be out of control. This is another example, 2 or 3 above 2 standard errors. Remember, from the center line to your upper control limit, you have 3 standard variations. This is 1, this is 2, and the third will be your upper control limit. Same for from the center line to the lower control limit. So if you see 2 or 3 above the 2 standard deviations, in this case, that could be a potential out of control process. Also, if you see 4 or 5 below 1 standard deviation or standard error, or if you see 8 points on one side of the center line. This is another example. Cycles are other. See, if you see the data and you draw curve, you can see that this is cycle. So this is a potential process that could be out of control. And trends, see, this is the trend, could be also indicate out of control process. So control charts helps us to understand if the process is in control or is out of control. Also, it helps us to understand or find out what is that out of control condition. So when a process is out of control, we have to find that special cause of variation. And depend on the type of control chart you're using, they will mean something. For example, if you use the X bar and R chart, patterns could indicate a change or jump in level, either for the operator, material, or machine. Or it could also be a trend or static change for equipment or worker skill. Or it could be if you have a recurring cycle, it has something to do with maybe the material or with the operator fatigue. If you have 2 populations, it could be material or machine quality. And if you have mistakes, it could be due to calibration or calculation. So analyzing the control chart is very important because they really mean something and they really help you to find out what is that special cause of variation.